In this video, we're going to look at a basic introduction to Venn diagrams. We've got a Venn diagram here, and we can see with this particular Venn diagram, we have two ellipses and a box. If we're dealing with probability, we say now that the box gives us the sample space, and we might have two events, A and B. So let's see an example of using a Venn diagram based on our previous video. What I'm going to say is event A, and we'll say now that this is going to be rolling a square number on a fair six-sided dice. Event B is going to be rolling an even number on a fair six-sided dice. So we'll have even and we'll have square. So taking my fair six-sided dice, we can list the possible outcomes. We could have a 1, a 2, a 3, a 4, a 5, or a 6. So where do each of these go? Well, let's start with the number 1. Is 1 square? Yes, it is. Is it even? No, it's not. So it's going to go in A only. If we look at 2, 2 is an even number, but it's not square. So that's going to go in B only. If we look at the number 3, this is neither square nor is it even, so it would go on the outside of the two ellipses. If we look at 4, it's both square and it's even, so it would go in the middle. We call the middle the intersection. If we have the number 5, it's neither square nor is it even, so it go on the outside. And finally 6 would go in B and B only, as it's even, but it's not square. So this has now filled out my Venn diagram. What we're going to do is look at some of the notation we use with Venn diagrams. The first one is what we call the union, the probability of A union B. This is the probability of A and or B. So if I wanted to shade that on the Venn diagram, it's all of A and it's all of B, including the intersection. And we read this as the union, or the probability of A and or B. If we now look at what we call the intersection is where we have the probability now of A and B. So the intersection, we say the probability of A intersection B. And that is simply the part in the middle. So if we look at this particular example, we can say that 4 is both square and it's even, so therefore it goes in the middle as the intersection. It's in both A and B. So that's some of the basic notation that we're going to use. In later videos, we're going to look at working with probabilities involving Venn diagrams, but for now, we just want to get a basic understanding of how to use them. Let's look at shading. So what we're going to do is look at shading some Venn diagrams. So on this one, we're looking to shade A union B. So this is A and or B. If we consider now, this is all of A, this is A and B, and this is going to be B, so we would shade like so. The next one is A intersection B. This is A and B, so we would simply have now the middle. This one right here says it's not A, but it is B. So we would read this as not A and B. So that means I can be in B just here, but not in A. That means that I can't have the intersection just here. If we look at this one here, this is A and B. So it's A intersection B, but it's not that. We saw in the last video the dash means that it's not. A intersection B is going to be this part right here. So if I have not that part, we're going to have now everything but the intersection. So all of this, all of the sample space, we're going to have now B, just B, and it's now going to be not A and B. So that is that part right there. So it's not the intersection of both. So let's just shade that, and obviously you would be doing a nicer job. This one is A and or B not. So this is A and B, as we've just seen, A and or B. So not is going to be everything on the outside. So this is just now the values in here that wouldn't satisfy event A or B. Okay, let's just look at this one right here. This is A and or not B. Often with questions like this, it's easier to consider two Venn diagrams. So what I'm going to do is just sketch this. So what we're going to do is have two and then put it back together. You certainly don't need this, but it might help you out. So what I'm going to do is put this on. This is going to be A and this is going to be B. This is A and this is B. So it's saying A, so we can put that on. So let's just put A on the first one. If I put A on this one right here, that is A. So A is all of this. If we now look at it's not and or not B, well, not B is going to be all of this right here. So if I put that on like so, that is not B. So not B is everything outside of B. So just jotting this on, we come up like so. So if I want A and or not B, I can simply put these two together. So I can see I'm going to have this part, and then I'm just simply going to be left now on here with the only clear bit. The only clear bit is going to be B only. So we can do that, A and or not B. So let's do that. We need the intersection right here. So that part's done, and then we're going to go on from here. As stated in later videos, we'll look at using the probability laws with Venn diagrams, but for now it's just getting a brief understanding of how to use these. So these are examples now of shading the given statements. Let's now look at some questions and we'll work through some of these. We're told a card is chosen at random from a pack of 52 playing cards. C is the event, the card chosen is a club, and K is the event, the card chosen is a king. We're asked to find these. So we're now looking at probabilities. So if we consider now our Venn diagram, this is going to be the sample space. So all values will be in here and all probabilities, as we know, equal 1. So what I'm going to have is the event C and the event K. Let's consider now what this is saying. These ones are going to be clubs. These are going to be kings. I know that I've got one king that is a club. That now is the king of clubs. That leaves me now 3 kings that are not clubs. We've got 4 kings in total, so we can put in here 3. If we just think about this now, we have 4 kings in total. 1 of them is a club, 3 of them are not clubs. If we think about the clubs, there are 13 cards. If I've got 1 in the middle, we're left now with 12 clubs. This part right here is C only. These are the clubs that are not kings. If we think about what's left, we've got now 12, 13, 16. That leaves me 36 on the outside, and this corresponds to the cards that are neither clubs, kings, or the king of clubs. So from here, we want to find the probability of K. If we just look at this now, we can say the probability of a king is going to be 4. We've got 4 of the 52, which you can, of course, simplify to 1 out of 13. That's absolutely obvious. We know there are 4 out of 52, and we didn't need a Venn diagram for that. If we now look at the probability of a club, again, straightforward. We can see on here there are 13 of those, so we can say 13 out of 52, which of course gives us 1 out of 4. There are 4 suits in the particular pack. If we look at this one, the probability of a club and a king, well, that's the intersection right here. So you could think of that now as simply how many kings of clubs have we got? Well, we've got 1. 1 out of 52. So the probability of a king and a club is going to be equal to 1 of the 52. This is where our Venn diagram helps. If we consider this one now, the probability of a club and or a king, if we look at this now, we can see in here we have 16 of the 52. So 16 of 52, and we can break this down. We can divide both of those now certainly by 4, and that's going to give me 4, and what we can have on here, 4 over 13. So probability of a club and or a king Just checking that, that's going to give me 4 over 13. Remember, these are not mutually exclusive events. We can have a card that is both a king and a club, and that's shown by this intersection. Something that's quite interesting, which we'll look at now, for mutually exclusive events, if I just draw a new Venn diagram, for mutually exclusive events, we would have something that would look like so. So these are now, let's just put this on. These could be examples, and we could have it anyway, lots of different ways to represent a Venn diagram. So for mutually exclusive events, we have no intersection. So this would be A and this would be B. So that's just a nice example whilst we're there. Okay, let's look at the next one now, the probability of not a club. Well, if we look at that now, we can see that quite clearly from there, the probability of not a club is going to be 1 minus the probability of a club, which is going to give us 1 minus 13 over 52, which is going to give us now 39. What we can have on there, 39 over 52, and we could simplify that if we like. So if we look at that, that's going to be, what's that going to be, dividing by 13, we're going to have 3/4, and that's fairly obvious. Not a king and a club. So if we consider this, it's not a king and it's a club, well, what we're going to have is 12. This part right here is the one that we're looking for. If I just go ahead and shave that. So this is the part that we want. It is a club, but it's not a king. Again, you might think of that in your head without using a Venn diagram. But we can say the probability now of not a king and a club is going to be on here 12 over 52, which we can simplify if we like. So there we go, using Venn diagrams for basic probabilities. Let's look at another one. We're told there are 25 students in a certain tutor group at Phillips College. There are 16 students in the tutor group studying German, 14 students studying French, and 6 students studying both French and German. We're asked to find the probability that a randomly chosen student in the tutor group A studies French, B studies French and German, C studies French but not German, and D does not study French or German. So this is where a Venn diagram can really help. So what I'm going to do is define 2 different events. I'm going to say that the event F, I'm just putting this here, the event F is going to be a student studying French, and the event G is going to be a student studying German. So this gives us our Venn diagram, and we can go ahead and do this. With these Venn diagrams, we always start in the middle. We can see that there are 6 students studying both French and German. The 6 must go in the intersection. So this would be now the French, and so if we did this as an event, this would be French and German. So there are 16 students in the tutor group studying German. That means that there will be 10 who are doing German only. If we consider there are 16 in total, 6 of them are studying both. 14 studying French, well 6 of them are already here, so the other 8 must be here. We're told there are 25 students in total. If I add that up, that gives me 24, so we can say there's going to be 1 on the outside. Only 1 student is not studying either French or German. So let's go ahead and answer these. So the first one is the probability of F. Well, that's nice and straightforward. The probability of F is going to be 14 out of 25. If we look at the next one, studies French and German, the probability of F intersection G, well, we got 6 of those out of the 25. If we look at studies French but not German, the probability of French and not German, which we could write like so, that gives us this part right here. So they're in French, but they're not in the intersection, and that would give us 8 out of 25. Does not study French or German, well, that's on the outside. So we could say now the following. So this is going to be now the probability of French and or German not. So this is on the outside, and we can write that that is 1 out of 25. So if we look at French and German over here, this is the union. So we've got now on here, that shouldn't say fug, it's just F, union G, not. So that's how we could use it. We don't need to use this terminology as such, but I think it's interesting nonetheless. Okay, let's have a look at this one. There were 125 diners in a restaurant who were surveyed to find out if they had ordered garlic bread, beer or cheesecake. So we're told 15 diners had ordered all three, 43 had ordered garlic bread, 40 had ordered beer, 44 had ordered cheesecake, 20 had ordered beer and cheesecake, 26 had ordered garlic bread and cheesecake, 25 have ordered garlic bread and beer, and it says a diner is chosen from random. Find the probability that the diner ordered A, all three items, B, beer but not cheesecake and not garlic bread, C, garlic bread and beer but not cheesecake, and D, none of these items. So let's go ahead and label these. So what I'm going to have are three different events. I'm going to have G, which is now ordering garlic bread. So I could say now the event. Remember, all we're doing is representing these with the ellipses. G is the event, and this is going to be now ordering garlic bread. So ordering garlic bread. And of course we can say that the next one, beer, B, the event B is ordering beer. If we look at the next one, C is the event ordering cheesecake. With this particular problem, we start in the middle. 15 diners had ordered all three items. So in now the intersection, this is the intersection of all of them, we put 15. What we're now going to work on are the pairs. So I'm not going to look at these just yet, I'm going to consider these ones right here. 20 had ordered beer and cheesecake. The intersection of beer and cheesecake is here. We need to be careful. A common error is to put 20 in here, but we've already got 15 who have all three items. So all I'm going to do is put in this one that it's 5. So we can see 5 have beer and cheesecake only, 20 have beer, cheesecake and garlic bread. 26 had ordered garlic bread and cheesecake, so garlic bread and cheesecake is just here. I've already got 15 here, so we must have 11 here. 25 had ordered garlic bread and beer, 15 of them here, we must have the other 10 just here. We can then go back now to these single items here. So we start with the triple, then we have the double, now we're looking at the single. So 43 diners had ordered garlic bread. So if I look, I've got 10, 15 and 11, that gives me 36. 43 leaves me 7 over. 44 diners had ordered cheesecake. Well, that's going to give me 31 in total. So that's 20, 31. So this must be 13. If we now consider the ones who ordered beer, we're told here that 40 ordered beer, 10, 25, 30. So this must give me 10. We need to finish this off, and the ones on the outside are those that didn't order anything. So if we look at this, we've got 125, so 20, 27, 38, 53, then we're going to have 58, and that gives me now 58 and 13, so 58 and 13 is 71. So on the outside now, let's go ahead and put that. So we've got 71, so what's that going to give me? A total now of 54. So let's just check that and we'll go through that and make sure we've got all of the correct values. So that looks pretty good. That gives us all of our values. Let me just add these up to check that I've got 125, 20, 27, 38, 53, 58, 71. That's going to leave me now 54 in total. So we want now the probability of all three items. So we could write this now as the probability of G, and we can say B and C. So this gives us the intersection, and we can say that is 15 over 125. We can of course simplify that if we wish. I'm going to leave it like so as it's a probability, but you might want to simplify it. Beer but not cheesecake and not garlic bread. So this is beer only. So we can say that the probability of beer and not cheesecake and not garlic bread is going to be equal to the 10 over the 125. If we look at the next one, garlic bread and beer but not cheesecake. Garlic bread and beer is going to be this one just here and not cheesecake. So that is going to give me now again garlic bread and beer but not cheesecake is 10. So we've got now garlic bread and beer but not cheesecake, and we'll put that in, and that now let's put that on as 10 over 125, which of course we can simplify. We can certainly divide by 5, so that would be 2/25, or what's that going to be, 0.08. I'm just thinking that sounds about right. None of these items, so the probability now of all of them, so the probability of garlic bread, when we'd have the union with beer and the union with the cheesecake not, we've got 54 out of the 125. Remember, with probabilities, you can either write these as decimals or fractions. I've not simplified some of those, I will leave you to do that. But that's just given us some idea on how we can use Venn diagrams. In later videos, we will look at some of the probability laws associated now with Venn diagrams and look at answering a range of different questions.